Okay, I think we could start. So if you have no questions about the previous lecture, so just to remind you, in the previous lectures, we have seen that if we have a function phi of t, and we would like to represent it by a basis, or not a basis, by a set of functions that we denoted as beta I of t, then the trick to do that is to project these phi's onto these betas. Okay, so this was the projection process, and then to sum from I equals 1 to a small number n, and this n can vary. I mean, if there is a bandwidth with a specific capacity that allows you to send many bits, I mean, a large amount of information, then this n should go to infinity. In which case, you would probably represent your signal in quite an accurate way. However, when the bandwidth, when the number of bits, when the number of numbers that you're allowed to transmit along this channel is limited somehow, then this number n would be smaller, probably even a single number, and therefore you would like to somehow pre-order your betas so that you will do something clever when submitting these scalar coefficients. Now, before starting this lecture, I viewed what we talked about in the previous lecture, and I noticed that I didn't fully understand the question of, I think it was Barak at the time, who asked, for each and every function, you may have to choose the betas in a different order. Why? Because the energy of the error would be smaller the more phi is similar to beta. And one phi could be similar to the first beta, and another phi could be similar to the 10th beta. And therefore, in the second case, you would like to first of all project onto the 10th beta. And then you will have to code not only the coefficients, but also the index of the coefficients. I mean, if it would be the first coefficient, you should order 1 and then the number of the projection. And if it would be the 10th beta that you have chosen to be first, then it would be 10 and the number of the coefficients. This kind of coding of submitting the number of the coefficients is something that you would find in wavelets, in sparsity, and we will not deal with it in this course, not because it is not interesting, but rather because we have enough on our table even without it. What we would assume is that somebody forces us to reorder my functions a priori. And then I would like to be as efficient as possible, even by just truncating the number of coefficients that I'm transmitting, even without being able to pick up the right betas for the specific signal, okay? So it is possible to order the betas for each and every signal that I'm getting. This is part of sparsity and compressed sensing and all this field of research. However, from a practical point of view, I don't know for which field applications it is being used right now. Probably the only commodity application you would find it would be MPEG. I think it would be MPEG 2000, where they use a family of a basis. It's not a basis, a family of functions which is called wavelets, and then you pick the index of the wavelet coefficient that you're transmitting with, and then you would allow this kind of picking up the right I for each and every signal. So this is probably the only field application where you would find something like that. But again, I'm not familiar with other stuff that may use or may not use stuff like that. Okay, so now we are limiting ourselves to the classical, what you would find in JPEG, in the classical JPEG and MPEG. And in fact, in most engineering applications, you would find this pre-ordering of the betas and then using them as a pre-order set of functions that you are allowed to use. Okay, so now we are ready to do the following. what kind of beta should we use? So the first ones, and we started talking about it in the last lecture, would be those that are defined as follows. So this would be my interval on which my psi is defined. So it would be something between 0 and delta, or 0 and 1. It depends how you'd like to refer to it. And say that I split it into capital N small intervals. Okay, so I have n of those, 1 to n. And for each interval, I define a different function. So this would be my first function. So this would be beta 1. Beta 2, I will plot it in blue, would be that guy. Beta 3, I will plot it in green, would be that guy, etc., etc., etc. So each beta would have a support on delta I, on this interval, which is delta with size delta divided by capital N. And this would be the support, and it would get a constant value at the top and 0 elsewhere. Now, in order for my beta to be orthogonal to one another, I need the inner product to be identical to the Kronecker delta. What we can do now is, with this kind of piecewise constant functions, we can build other type of piecewise constant function. In a moment, we will see how. In order to do so, let me first of all remind you of what is the inner product between two vectors. So assume that I have two vectors. This is vector A and this is vector B. Each one has n components. Now the inner vector is defined as the transpose of A, which means writing A like that, and if A has complex numbers, also negating, conjugating them, and then multiplying by B that looks like that. Okay, so this is the inner product of two vectors. If the inner product is equal to 0, then we say that the two vectors are orthogonal. Okay, so this is just a reminder of something that you should have learned in algebra. Okay, now an orthogonal matrix, we say that U is an orthogonal matrix if the product of U transpose U is equal to U transpose, which is equal to the identity matrix. Okay, and then if you write U explicitly like that, where each and every column here I can write as U1, U2, etc., then with the above property, what I can prove easily is that if I look at the inner product of U1 and say this would be Uj, then the inner product would be 1 if I'm choosing the same. If I'm looking for the inner product of U1 with U1, it would be equal to 1. Otherwise, if I'm choosing a different index here, if there would have been 2 here, then it would be equal to 0. Okay, so the columns of this matrix would be orthogonal to one another, and the same would hold for the rows. Okay, and so the rows and the columns for a matrix that satisfies these equations are orthonormal to one another. And we say that such a matrix is called a unitary matrix. Okay, it's a unitary matrix, and it spans the basis Rn or Cn if it is complex. Okay, so
can I ask a question?
Sure.
Well, can you repeat, please? Why was it the square root of n before in the previous slide or two last slides? It was an example for.
You're asking,
yeah, like the first row here says square.
You're asking why am I having this one here? Yeah?
Yeah.
Okay, so let's see of what happens to the interval 0, 1. Okay, after I sliced it, so this is the interval 0 and 1. This is my time. And I split the interval into capital N intervals. So what would be the size of this guy? It would be 1 over n, okay, times 1, okay, because the interval is 1. Are you with me? Sorry, let me just redraw it. So the size of each interval, I zoom into it, is 1 over is 1 over n. Now, there is a constant function that is going on here, and it is 0 elsewhere. Okay, this is my function. And I have this unknown number that I have to define here. And the question is, what should be this unknown number? Let's pick, without loss of generality, let's pick it to be 1. Okay? And now let's see what would be the integral, the inner product of this function with itself. So the support would be just between 0 and 1 over n. You agree with me? So it would be 1 over n here. And there would be 1 times 1, okay, dt. So the result would be 1 over n, okay? And therefore, the inner product of bi and bi would be 1 over n. In order for it to be orthogonal or orthonormal, in order for this value to be equal to 1, I need to plug in here square root of n, and here also square root of n, and this would guarantee that multiplication of square root of n by square root of n would be n, and therefore I could cancel it with the support, with the distance, with the time interval that I have here. Did I answer your question?
Yes, thank you.
So this is the normalization factor that I have to push in, so that my functions, my functions that I will be using would be orthogonal or orthonormal. Orthogonal, they are orthonormal to one another. Okay, so now we have this function, and let me give you an example of such a matrix. Let's look at the identity matrix. So the identity matrix, if I take each and every column in the identity matrix, okay, so I take this one and I call this one E1, and I take this one and I call this one E2. So this is how they would look like. Just to remind you, an identity matrix is a matrix that looks like that. Okay, it would be 1 along the diagonal and 0 elsewhere. And what I can do is I can write each and every vector as a linear combination of the identity matrix. Okay, why? Because the identity matrix spans the whole set of n-dimensional of Rn, basically. Okay. So any vector in Rn can be spanned by these by projecting the A's into these EIs. Let's see what is going on. And now the inner product between two vectors is nothing but the conjugate of the first vector, which I can write as such, and the second vector. So again, just to remind you, the conjugate of one of the elements of the identity matrix would be nothing but the transpose of this vector. Okay, so this would be the first, the second would be this one, so this would be E1 conjugate. Okay, the second one would be this one, etc., etc. Now let's open these two brackets. Okay, so what is going on here? So I open these two brackets and I'm pulling all the summation outside of what is going on outside. So I have sum by I and sum by j of AI bj times EI transpose EJ. Now let's zoom at what is going on here. Here I have the inner product of EI and EJ. And we know that the inner product of the trivial basis of the of these rows or columns of the identity matrix is equal to nothing but the delta ij. I mean, it would be equal to 1 if I is equal to j and 0 otherwise. So I can write it as such. Okay, so I just replace it by delta ij. Now remember that this delta ij is summing over the coefficients only when I is equal to j. So I can eliminate one of the sums. So if I eliminate one of the sums, because the delta is basically filtering out all the beta i's that are not all the beta i's all the beta j's for which j is not equal to I. So I just end up with the following inner product. So we started from the inner product. We write each and every vector as a linear combination of the trivial basis of the base of the eigen of the rows and columns of the identity matrix. And at the end of the day, what we get is by definition the inner product. So there is nothing complicated about it. Okay, but now we are ready to start manipulating our functions in some interesting way. the same claim that we did about vectors, we can actually make about functions. I mean, we already did. And we said that two functions are orthogonal or orthonormal if the inner product between them is equal to the delta function, to delta ij. So only if I equals j, I will have the solution of this inner product being equal to 1. So this is the definition of the inner product between two smooth functions, in this case defined on the interval between 0 and 1. Okay, so this would be beta 1, beta 2 would be something else, and what we are looking here is the definition of the inner product. Okay, now what we would like to do is use the properties of the unitary matrix, of any unitary matrix, in order to blend, to somehow combine these betas, this family of functions beta, into a new family of functions. We'll call it F. And how do we do that? We do that by multiplying the betas by the entries of the unitary matrix, and we call this unimatrix matrix R, U, and the indices would be R and I. So what I'm doing is let's call it linear combination, Fn combination, call it whatever way you like to call it. But what I'm doing is I'm taking my orthonormal functions beta, and I'm looking at a linear combination of them that would give me a new set of functions, and let's see what we can say about this new set of functions. Okay, so again, I have a set of orthonormal functions betas. I have a unitary matrix U, and I'm translating these betas into F's by some linear combinations of these betas. And the interesting thing is that we start from continuous functions, and we end with continuous functions, with smooth functions that are defined between 0 and 1. What else do we have? We have that the U's, okay, the columns or the rows of the unitary matrix are defined as such, okay? So one row or one column, if you multiply it from the right, would be the generator, the way of linearly combining the betas. Okay, so what is the theorem that we would like to prove here? What we would prove is that the new basis that we have just constructed, not basis, the new set of functions that we have just constructed are also orthonormal. Let's prove it. It's not a big deal. This is the inner product between Fi and Fj, and we write it explicitly. So this would be the Fi times the conjugate Fj. Okay, and now since we have constructed Fi as a linear combination of the betas, we can write it explicitly. So we have an index that runs over the matrix, the right vector of the matrix that multiplies beta. And we have, and remember, it would generate Fi by picking up the right row or column in U. Okay, so this would generate Fi. And we do the same for beta. So the running index would be L, and the F that I would get would be Fj. Now, we can use the linearity of the summation and the integral, and first of all, pull all the summation outside of this multiplication, and then push the integration inside so that it integrates over betas. And we know that the integration over beta times beta transpose is nothing but the inner product between the beta. So it would be beta R inner producted of T, inner producted with beta L. This should be R of T. And we know this is given to us that the inner product is nothing but the delta function, okay? So we have the delta function. Now, what do we do? What do we know about the rows or columns of the unitary matrix? You know that the unitary matrix has orthonormal rows and columns. Now, since we have the delta of R and L here, what we can do is replace this summation only for the set of indices for which L is equal to R. Okay, and if we do that and we call this new summation K, then so again, the L and the R are replaced by a new index, which we call K here. And now what we can do is sum over the K that runs on UKI and UKJ. And at the end of the day, what we got by definition is the inner product between these two vectors. And we know that since we started from a unitary matrix, what we get is nothing but delta ij. Okay, so in fact, if we start from an orthonormal set of function, beta i's, and we use a unitary matrix to blend it, what we get at the end of the day is an orthonormal set of functions. So this is an interesting observation. It would allow us to start from a set of any smooth function that we would like and manipulate it so that it would fit our needs. And let's see how we can do that. There is also an alternative proof in which what we do is we write the F explicitly as the betas that multiplies the unitary matrix. And then we can also have the conjugate, the conjugate of these guys written as such. If I just take this and write it as conjugate, then this is how it would look like. And now I write the inner product explicitly, and at the end of the day, what I would get is an identity matrix, which indicates that only when I do the inner product of fi with fi, I would get identity. Otherwise, if I take f1 and inner product with another function, then I will get 0. Okay, so this is an alternative proof for the same argument. Now, this construction is important because we'll use something like that later on. So it is important to show it to you. Okay, what else do we need to say here? If we, for example, look at the inner product between all functions to all functions, then each and every the inner product of each and every function would give me a delta function, and summing over these n delta functions, I would get a number n. Okay. Now, just to remind you some more properties about unitary matrices. If I'm multiplying two unitary matrices, this is just usual multiplication of two matrices with the conjugate, with a conjugate inside. Then this is an identity that I would get anyhow. But what is even more important is that if I multiply this couple with this couple, I'm now opening it. Okay. And now here I have a multiplication of two unitary matrices, and we know that multiplication of two unitary matrices is nothing but one by definition. Identity, sorry. So I plug in the identity. The identity times any matrix would give me the same matrix. So at the end of the day, what I would get is that multiplication of two unitary matrices would give me a new unitary matrix. Okay. So I proved to you that multiplication of two unitary matrices would yield a unitary matrix. So if I blend my functions one way and I have another way of blending them, and these blendings are legitimate in the sense that they are unitary, I could do whatever I like. Okay, so remember that in order to represent a given signal psi of t by these betas, I had to multiply it with these coefficients, scalar coefficients we call psi beta. Representing psi with a different set of functions, I have to find out what would be the new coefficients. So if here instead of betas, I would write my fi's. Okay, so here I have my fi of t. Then the coefficients would not be psi1 beta, but I would rather call it psi1 of f. Okay, and the question is, what is the relation between these psi's and these f's? What are the relations between the coefficients of representing my signal with one set of functions and then with a different set of functions where I know what is the linear relation, the matrix relation between these two set of functions? Recall that the f's are defined as beta times u. So what can we do in order to find out how the coefficients of f would look like? I just have to do the inner product. And this is what we'll do. So we know that the psi t is equal to beta, to the beta functions times the coefficients. Okay, this is something that we know. Now I do nothing. I just plug in an identity matrix in between. It would do nothing. It would have zero effect. Now I expand this identity matrix into two unitary matrices. Okay, I allow to do that because I know that there is an identity, that multiplication of two unitary matrices would be nothing but U times U transpose, U conjugate. Now I know that this beta times U is nothing but the F's. So immediately I'm getting that the new coefficients, the F coefficients, are equal to nothing but U conjugate times the previous coefficients. So it's not a big surprise that the new coefficients of the new set of functions, F set of functions, is nothing but a related linear transformation of the previous coefficients, of the previous scalars that I used. Okay, so these are all preliminaries. This is all the background for what we are about to see. So remember, until now, what we had is we have seen one not so interesting family of orthonormal functions. This was the set of functions that had a support over this 1 over n, and therefore the value of this function was nothing but 1 over square root of n, so that the multiplication would be equal to 1, the inner product. And we denote this, I mean, when I have this function, when this is 1, okay, this is 1 over n, then I call this function 1 boldface 1 over the interval delta I, okay? And this is why I had to multiply it by 1 over square root of n. Sorry, this is why I had to multiply it by, this is why I had to multiply it by square root of n, okay? Okay, so now what can we do with this set of functions and the fact that I know that if I use any u and multiply this set of, let's call it the standard basic, okay, standard, the standard the standard set of matrices, set of signals, what happens when I look at this beta standard and multiply it by any orthonormal, any unitary matrix Q. Okay, so this is the question, and this is what we'll try to answer. Okay, let's start with a very simple way of constructing interesting signals. And before that, let me give you a motivation of why I'm actually revisiting my set of beautiful signals that look like that. Okay, assume that I have my, so these are the basics, not the basics, these are the family of functions that I'm playing with, and assume that my functions are something that are completely random in the sense that I don't know much about how they would look like in the interval between 0 and 1. Now assume that somebody is telling me, look, you're allowed to represent these functions with a single number. What would you do?
Take the average.
Who was that?
Liran.
So Liran is saying, take the average. And you're right. So the first function that I would like to inner product with this guy would be nothing but, now you should tell me what should be the value of this function so that the inner product of the function, let's call this beta function, a constant function of this beta 1 with itself would be equal to 1. And remember, this is 1. So what would be the value here?
1.
1, okay. So the most trivial function would be a constant function that would allow me to do the inner product of this one with that one. This would be the coefficient, so it would be the average of the signal, and it would multiply my beta 1 of t, which would be nothing but a constant. Okay, so So this is my first order approximation for n equal 1 of this function with this kind of a basis. Now assume that somebody is giving you 3 functions, or sorry, 2 functions to play with. The question is what you would do. I don't want an answer now, but just start imagining of how should you build clever set of functions in order to represent arbitrary given functions where, again, where all you have now is just the fact that they are completely random, you know nothing about them. So picking up this kind of selection is somewhat arbitrary because saying that the first function would just allow me to represent this part of the function and basically ignore the rest of my support is somewhat arbitrary, and this is probably not something that I would like to do. Okay, so just having one function here is probably not what I would like to do, but still, it is a very elementary basis to start with. So the question is, how do I re-engineer my my basis function? So for that, we learn about 3 families. That would be the introduction to something which is a little bit more sophisticated. And let me just go and show you what would be the first one. So first of all, let me define the Hadamard or the Kronecker product of 2 matrices. So I have a matrix A of size m by n, and I have, so m would be this axis and n would be that axis. And I have similar, another matrix B of a different size, P by Q. And the Kronecker product between these 2 matrices is nothing but taking each matrix B and placing them at the places of the elements of A, where each matrix is multiplied by an element of A. So let me give you an example. And the example would be very specific. Now I define the matrix. Now, okay, so what would be the size of this matrix? The final size of this matrix would be m times p. I mean, it would be the multiplication of these 2 coefficients along this axis, and it would be n times q along that axis, okay? Because we have to put, so if these are the A elements, and these are the B matrices, so instead of each A element, I'm putting B matrices, so I have to multiply. For example, let's call it the x-axis, which is the second term here. So I have to multiply the size of this matrix, which is Q, times the number of elements, which are m. Okay. Now let's give a specific example. Let's define something that we will call the Hadamard matrices. A matrix, which we call a Hadamard matrix. And it would be defined in a recursive way, okay? And how do we define it? First of all, the smallest Hadamard matrix would be a 2 by 2 matrix, and it would look like that. It would be 1 over square root of 2 times 1, 1, 1 minus 1. Okay, so this is the most basic one. Now the h2 to the power of n plus 1 matrix would be taking the 2 matrix, the 2 by 2 matrix, and making an Hadamard product with the Hn matrix. So this would be the way of increasing from a matrix of size, I don't know, 4 to a matrix of size, it would be 4 times 2, 8, okay? Or 2 to 4 for that argument. So this is writing this guy explicitly. So I'm just plugging in the 2 by 2 matrix with the Hadamard product of that matrix, which I don't know yet how it would look like. And this is how the Hadamard matrix of size 2 to the power of n plus 1 would look like. Now let's give some some concrete examples, okay, so of how they would look like. Okay, so again, so this is how it will be built, and before we'll see how they look like, let me just give you a theorem that for any given n, h integer, okay, and it's integer, h 2 to the power of n is unitary, and obviously real and symmetric by construction. So how do we prove the unitarity? So the unitarity would be proven by induction, okay? So first of all we need to do is take the 2 by 2 matrix and multiply it by itself and see that h times h2 conjugate is equal to 1, 1, 0, 0. And it is quite easy to see. And then we'll have to use this initial step and prove by induction that that it would hold for any n. Okay. So first of all, what we do is we look at the multiplication of two matrices of size 2 to the power of n plus 1. Okay, and if I write it explicitly, I have 1 over square root of the first and 1 over square root of the second, so I get 1 over half. Okay, and now I have the relation between this guy and the previous one is given like that. Okay, so this is the first one. So this would be the first one, and this would be the second one. Now remember that we assume by the induction step that for h 2 to the power of n, I have unitarity. So this is my induction assumption. And therefore what we do is we have that, let's just examine this part. What I have here is h that multiplies this one, and therefore it is identity, plus this guy that multiplies this guy, and therefore it is identity. And therefore what we get is the following. What we get is the following set of matrices, where 0 here is in fact a matrix of size 2 to the power of n by 2 to the power of n. So this would be a 0, a huge 0 matrix of 2n by 2n. Okay.
That's supposed to be conjugate.
Conjugate?
Like this. Yeah, the second matrix.
Again?
Yeah, exactly. Doesn't it supposed to be like first matrix not, but the second one when we multiply?
What is the conjugate? What is the conjugate of a symmetric matrix, which is real? It's nothing but the matrix itself. So this is in fact the conjugate of itself. Okay.
Oh, okay.
If I have 1, 1, 1, minus 1, the conjugate of that would be equal to itself.
Okay.
Okay. If I would have a complex number here, I would have to change signs. If it would not be symmetric, I would have to flip about the diagonal. Otherwise, it is like that. So what I proved is that this is indeed the identity matrix, because what I have here is 2 times I and 2 times I divided by 1 over 2, and eventually this is what I would be getting. So it is symmetric and real, and since we have the starting point by which multiplication of the two smallest Hadamard matrices is equal to identity, then the proof is complete, okay, by induction. So any Hadamard function is any Hadamard matrix is a Hadamard matrix. Now, what do I need these matrices for? Let's see how they look like. What you can see here is that if, for example, let's just look at this very simple matrix, and for example, assume that I have my my standard smooth functions defined as 2 functions like that. Okay, so I have, for example, 2 functions like that. If I use this unitary matrix in order to blend my standard basis, what I would get, anyone has any idea? How would the new functions look like?
2 orthogonal mixes of the 2.
Yeah, but how would these mixes look like? I think that you can actually paint on the slide if you want. So this was, let me just remind you, this was my first, and this was my, these were my betas. And now I blend them with that. how would they look like? I have two functions. Obviously, because I started from 2 and I have this matrix, I have two functions. So how would yeah, you are right. So this is, what was that?
Barak.
Barak. So what Barak is saying, that the first function would be a constant function, which is what I told you I would like to expect when I'm Barak. This is the point. So tell Tom to add a point to the homework. So the constant function is what I would like to have. Okay, if I have a single number to represent my function, then probably I would like it to be constant. And the second one would be a function that looks like that. So it would be minus here and plus there times the right coefficient. But you can see that these two functions are orthogonal to one another. And they somehow represent the fact that with the first number, I capture almost everything in the signal. And with the second number, I just add the information by splitting my 0, 1 domain into 2. Now, let's see if these Hadamard matrices are doing that. So we proved that, and we gave, let's see how they look like. So this is how the Hadamard 2 looks like. This is how the Hadamard 4 looks like. And you can see that here, the second term, I have 3 changes of sign that would in fact, that would imply that I have 3 changes in sign when I would build my function. Here I have only 1 change of sign, and here I have 2. So I have 0, 3, 1, and 2. And this is not exactly what I have wished for. I would like to have the second row or the second column to have probably 1, and the next one to have 2, and the last one to have 3. I mean, this is how I would expect my, it's called sequency, the number of changes of sign when I walk along my signal from left to right, along my coefficients by which I'm blending my signals from left to right. So this is what I'm getting, and this is probably what I've wished, what I would have wished for. Let's see how it looks for 8. So in 8 here I have 0, and here I have 1, 2, 3, 4, 5, 6, 7. Here I have 7, and this is terrible. It is terrible, and you can see it here at the bottom. Let me zoom in. You can see here how the sequence looks like. So I have 7, then 3, then 4. And if I would have liked to do something which makes sense from an engineering point of view, I would probably like to order these sequences so that this line would be probably the only, well, let's go backwards. So that this row should probably be here last, okay? This row should probably here. The 2 row should probably be there, etc., etc. So what I would like is the frequency, the way by which I'm splitting my signal. I would like it to be to have some rational order to what's going on. Why? Because if I represented my signal with a constant function first, then the next logical thing would be, if my signals are random and I don't know anything about it, is to split my domain into 2 and do the best I can in order to represent everything that is going on, say, in the first half or the second half. Otherwise, I will pay a lot if I just focus my my representation power at just a limited part of this sequence. Okay.
Can you please explain again what is the sequencing and what are you counting here? Like, what is the 0, 3, 1, 2? Sorry, I lost it.
Okay, so let's go back to the first one. What I'm looking here, what I'm doing now is traveling from left to right and asking the question, how many changes of sign do I have when I walk from this one to that one? Here I have 0, okay? There is no changes of sign. Why is it important? It is important because when I blend my standard functions afterwards, remember, here comes my first function, and here would come my second function, okay? And the fact that I have 0 changes in sign means that I would blend these two together by just mixing them into a function which would be a constant function. Okay? Now let's explore the second row here. When I'm moving, when I'm traveling and log the coefficient of the matrix from left to right, what I have here is a change of sign from 1 to -1 here, somewhere between these two numbers of the matrix. Okay? What it means is that the next function that is blended that is taking the standard set of functions and blending them would look like that. And this is probably something that I would like to have when I have only two functions to represent my functions with. The first one would capture the average of the function, and the next one would split my domain into two and would tell me, look, what you have here is that you can probably do with just the average of either this one or that one. Okay, so the next one would allow me to represent properly, or to add more information about something which I assume to be a constant number here and another constant number there. Okay, the set of functions that I would be able to represent with such functions are functions that looks like one constant and another constant. Okay. Now, if I have more coefficients, I would probably like to split my domain and to add more fine details to the way that I'm allowed to represent functions. If I now add another layer to that, I would probably like to be able to represent in a finer grade, etc., etc. So the more ends I'm adding, the larger my number of functions, the number of functions that I have, the finer the resolution that I would be able to take. And my claim is that the Hadamard functions allow me to do so. But I'm showing you that it allows me to do so, but it's not so. I mean, I'm paying some penalty here, and the penalty is the fact that the sequences. So this here I have a sequence of 0, and here I have a sequence of 1. Here I have a sequence of 0, and here I have 1, 2, 3. And I would have expected. So there was a comment by somebody I can't see. So if you have any comments, just say them, because for some reason I can't see your.
No, he just wrote that someone is with the mic on. That's all.
Oh, okay. Let me just see how can I see the discussion. Chats. Okay, now I can also see the chats.
Can you explain, please, why the order matters?
Yeah.
I mean, we get the.
So let's assume that all I have is two functions, okay? And let's go for H4, for example. Okay. Now, what do I have? I have one function that is the constant number. So if I have just one number, I can take the average of everything. And I have a second function that looks like that. It looks like that. Okay, something like that. This would be my second function. Obviously, they are orthogonal to one another, and they can span something, but they span something which is strange. I mean, it would span all the functions that have a positive. I mean, some value here and another value there. I mean, it is spanning a space of functions which is, in my sense, are not natural. Okay, so I'm taking the average of all the numbers here with all the numbers there, and the average of all the numbers here and all the numbers there. And with that, I need to reconstruct something and just try to imagine what can you do, what is the set of functions that you're allowed to represent with these two functions. Now, I mean, try to draw in your mind what can be done here. Now, if from some other reason, what I would have had is, this function, then I can understand what is going on. These two functions allow me to reconstruct all piecewise constant functions, okay? These and that. So it makes more sense to pick up these two as the first function that I have rather than these two.
because we want at each function to have more and more details?
Yep.
Okay.
Remember that the game now is to have my error, my representation error, decrease as the number of functions that I'm allowing to represent. So it has the energy of the signal here, and then I would like it to be as rapid as possible. So if I would choose wrong numbers, the error would look like that. I mean, at the end of the day, it would probably end up with the same number. Obviously, this should go down, but I would like my selection of set of functions to give me the most rapid way of decreasing my energy, the energy of the error. Now, it is true that if my function happens to be piecewise constant like that, then obviously picking this one as the second one would probably make the day. Okay, so if this would have been my family, of functions, this would make sense. But this is not a probable way of looking at signals. Let's for the time being look at what is going on with H8. H8, the sequency in the same manner looks like that. Okay. And the question is, what can we do in order to fix it? So you don't yet understand why should we fix it, but let's assume for a moment that I'm telling you in order to fix it, I need to look at the sequences in an increasing way. Okay, this is what I would, for the time being, take it for granted. This is what I would like to have.
Maybe a permutate matrix.
Again?
A permutate matrix that will.
Well, you can permute the matrix. This is obviously what we will do, and but let's do it one step at a time. This is how the H16 looks like. Let's see. So the first one is 0, and now let's see what is going on here. 1, 2, 3, 4, 5, 6, 7, 8, 9. I assume that what you'll have here is probably 15. But again, you're welcome to check it at home. So how do we fix it? I mean, how do we make it? Okay, so there is a challenge here, and this challenge that Freddie made, and the question goes like that: take a Hadamard matrix of this size. What you need to prove is that all sequences appear in the rows, okay, in some order, okay, where the first row sequence is always 0. So this is the easy part. Proving that all sequences appear over there is the more complicated part, but it can be done. And the reason that Freddie is introducing this question every semester is because there is a very tedious and cumbersome proof of that. And if you find an elegant and short one, it would be really, we would be really happy to include it in the lectures. So there is a dirty long proof that we will not include here. And if by some magic you find, as a side note, an elegant proof, we'll be happy to present it. And you'll get some credit for that. Okay, so what is the Walsh-Hadamard? The Walsh-Hadamard is exactly the idea of taking the rows, and if you do it for the rows, apparently you do it also for the columns, by reordering the rows or the columns so that the sequency is increasing. So what you see here is the sequency which is equal to 0. Here the sequency is equal to 1. Here I'm pointing the points to which the sign is changing. The sequence is equal to 2, and here it is 3. So the Walsh-Hadamard matrix is nothing but taking the Hadamard matrix and ordering the rows, shifting the one sequence to the top, and so this is 3, and the highest frequency or sequency to the bottom. Okay, and this is how the Walsh-Hadamard matrix of size 8 would look like. And again, now we can actually see the structure in this matrix. I mean, if we look at the sign and we plot this one as this guy and that guy as that kind of a signal, and this one as this kind of a signal, and this is actually what this matrix would do to your standard basis. So this would actually be your new basis when operating on the standard basis. We call it the standard basis. Okay. So if the standard basis we started with was like that. Applying the Walsh-Hadamard matrix would give me a new basis that would look like constant. Now it would look like that. The next one would look like that. And the last one would look like that.
The third one is upside down, isn't it?
The what?
The third
Yeah,
one.
this one is upside down, you're right. Let's see if I can use the, yeah, this one is upside down. And usually we say up to a sign. Okay, so this is like that. Okay, and now the question is, why is it good for, I mean, why do we actually need these sequences? I mean, why is it important that, just open the window. Why is it important that we are controlling this? Is it important? So let us just dive into it. And before that, let me just tell you that if we go back to the Hadamard matrix, so in fact, there is a way of representing each and every entry in the Hadamard matrix. Remember that there was this constant coefficient, and let's throw it aside. What we have here is the claim is that the entry of each and every Hadamard matrix is nothing but -1 to the power, and here comes the interesting part. We have the K and the L entries in the matrix. So assume that this is my Hadamard matrix, and this would be the kth entry and the Lth entry. Okay, so this is the element that I'm now inspecting. So it would be either 1 or -1, and deciding whether it would be 1 or -1 is taking -1 to this power. Now, what is this power? I write K in its binary form, and I write L in its binary form. Each and every integer can be written as a binary in a binary representation. Now, what I need to do is sum up the multiplication of these coefficients, okay? So summing over the multiplication of these coefficients would give me the power of the -1 that I need to take in order to get this element, okay? Is it important? No, it's not so important. It is important if you'd like a fast way of generating Hadamard matrices. So if you'd like a fast way of generating a Hadamard matrices, what you need to do is take the inner product of the binary representation of the indices, and then take -1 to this power, okay, to this number, and this would give you the right entry in the Hadamard matrix. So this is just a good to know way of how you populate your Hadamard matrix entries. Okay. Before we go into a 20-minute break, let me just tell you the following. What happens when I'm taking my Walsh-Hadamard matrix and multiplying it with the standard basis? So this would have been my standard basis, and this would have been my Walsh-Hadamard matrix. What I would get is now from a matrix and a set of continuous functions, orthonormal continuous function, what I would get is a new set of continuous functions. And this new set of continuous functions would be exactly as those that I've plotted before, okay? So what happens now is that I'm taking these functions which look like that, and the next one would look like that. The next one would look like that, etc., etc. And I'm blending them with the Walsh-Hadamard matrix. And what I would get is my new functions that would look like that. So this was the first one. The second one was something like that. The third one was something like that. And you can see that there is a nice property to this new construction of functions that would allow me to somehow split my interval each time into 2, hopefully, and achieve a better representation to my signal, okay? Now, let's see what happens from a coefficients point of view. Here I have my normalization factors, and here I have my normalization factors of the -1 and 1 Walsh-Hadamard matrix that we denote with a tilde here at the top. So these two coefficients go away, and what I have here is the plus and minus ones matrix. Okay, so this was the ones, and then I had 1, 1, 1, 1, minus 1, minus 1, minus 1. So this was the Walsh-Hadamard matrix, but throwing away these coefficients, and it multiplies the ones, these coefficients. Okay, so this is where the tilde is coming from. It means that the coefficients, that the entries of my matrix belong to 1 and -1. And what we note is that the normalization cancels out. Okay, so after the break, what we'll see, let's do it one bit before the break. So this is my Walsh-Hadamard, and this is how the functions, the standard basis looks like. Okay. And this is how the Walsh-Hadamard would look like. So the first one, assume that these are, so this is my time axis. And let me plot it, plot the three of them. So this would be my time axis for the different Walsh-Hadamard smooth functions that I'm looking for. And this is how the function would look like. So the first one between 0 and 1 would look like a constant function. Okay. The second one would look like a constant function until the center, and then it would be -1. The next one would be 1. Then it would go to -1. Then it would go to 1. So this would be the third one. And the fourth one would be 1, -1, 1, -1. So it would be, it should be at this, it should occur at the same place. Then 1 and -1 here. Probably I did something wrong here. 1, 2, 3, 4, 5. No, it should have only 4 of them. So I did something wrong here. So let's see, what did I do wrong here? So it should be like that. It should be like that. 1, -1, 1, -1. So this is how it should look like. Okay. So this would be my Walsh-Hadamard. So this should be Walsh-Hadamard 1. This should be the Hadamard Walsh 2 of time, etc., etc. Okay, and probably I would prefer to use these kind of functions to represent my signals if the only thing I know about them is that they are random. Okay, so before we take a 20-minute break, any questions whatsoever? Yeah. So if not, we'll be back at 10.
Let's
do it. Yep.
It looks like it looks good, but it looks like you're trying to get the piecewise analogous of the harmonics, the cosine and sine.
This is indeed, well, then until now, the name of the game was using only piecewise constant functions. But what Barak is saying is that, in a sense, why don't you just use sine waves? I mean, you have a sine wave like that. So it would be the first harmonic, and then the second harmonic would be probably something like that, etc., etc. You're absolutely right. At the end of the day, we'll see that the harmonics, that these kind of signals are in fact optimal if you order them in order to represent a very special set of functions. And I want to push this set of functions. So all functions, all signals for which I know that phi of t, we call it Dirichlet energy. For all smooth functions, I mean, for all these kind of functions for which the energy of the gradient is smooth, it appears that the harmonics, that the composition of this operator transport with itself, we write it like that sometimes, or we write it like that, or we write it like that. It depends how we, or we write it like d over dx squared plus d over dy squared. It doesn't really matter, or you write it like -1, sorry, like that. It doesn't really matter how you write these kind of operators. All of them have the same name. They are called the Laplacian. Okay, and if what is written here is basically, I mean, if I treat this operator, and sorry for waving hands, but for now it is just an intuition. You don't have to dive into it. If all you know is that your d psi absolute value is smaller than 1 in some L2 sense, then you may write it as d transpose psi transpose d psi smaller than 1. If this is the only condition that you have, then apparently the functions that you would like to have in order to represent these psi's in the best possible way would be the decomposition of this operator. And the decomposition of this operator would be nothing but the Fourier, if this would be the derivative. But if by some reason you know that the composition of this operator is different, for example, assume that you know the statistics of these functions, then this operator would have a completely different meaning. It would now be the autocorrelation, and the eigenfunctions of the autocorrelation matrix would be a different set of functions. This, and we'll call it PCA. So Fourier would be the decomposition that would give me the best representation way for all smooth signals. PCA would have the same meaning in the sense of representing all functions whose autocorrelation matrix can be decomposed. And the same structure would allow us to investigate new families of functions. So tomorrow you'll have a new family of functions, and you would like to know what is the set of functions by which I need or would like to represent my set of functions, and you will be able to analyze that. You will be able to come up with a solution to solve it. But wait with that. I mean, so we'll be back at 10:53. Okay. More questions? If not, then this is
Ron, can I have a question?
Sure.
In what way the new basis of functions are better than the standard functions?
Excellent questions. So let's start with that. And let me draw any. Assume that you have a signal. Let's draw it over here. So this is your signal. So Liran is asking the following question. I have phi of t between 0 and 1. Okay, this is what I know. And psi of t can be any function. I mean, it's a function. It's not. It's a function, so it is getting a single value. Now, let me ask you the following. Assume that I have a single function to represent it by. What would you choose?
The fourth will be the best.
The what?
The fourth, the one that goes up and then down. The fourth row.
So what would be the function? Again, I'm allowing you. So this is one function there, and we have many functions like that, and you don't know anything a priori about these functions. You know that they can get completely random numbers. Why? Why would that be your why would that be your representative function?
Because the function that you draw goes up and down 4 times in this.
No, but again, remember that I'm telling you that you know nothing about these functions. That they can be like that as they can be like that as well. They can be like that. They can be like that. I mean, they can be any arbitrary function. The only thing you know about them is that you don't know much. I mean, this is what you know. And the question is, what would you do? And the answer is that I mean, think about this function as a set of random numbers. Okay, this is the set of random numbers. It's continuous, but think about them as random numbers, and you know nothing about them. I mean, probably you know the range of them. They would be between 200 and minus 200. But this is the only thing that you know about them, only the range. How now you're allowed to represent them by a single function. What would you do? And probably the most clever thing from an MSc point of view would be somebody.
Yeah, the average, the constant function that is the average.
The constant function, okay? So if I have the constant function, then the constant function, when I hit it with respect to the psi function, would give me the average, okay? And this is very important thing to know. If I have only a single beta to use, take the average. The harmonics would also give you that. Now assume that some oracle is telling you, look, you're allowed to have a second function. So you know what is the average. But now you're allowed to have a second function. What would you do? Then let me tell you what would probably be the answer. The answer would be, I would like to know the average into, I would like to split this large interval into 2, 0, 1, and know what is the average in the first and what is the average in the second, okay? And it doesn't really matter how I split it. I would just like to know what is the average in the first and what is the average in the second, and then everybody would be happy. And the best way to do it is probably to do something like that. I mean, to have a function like that. Probably. Or a function like that, it doesn't really matter. Because if you have these two and they're orthonormal to one another, then they'll probably span the same piecewise constant functions that go between 0 and 1. And 0 and 1. And this is really, really important. I mean, if you know nothing about the signal, then somehow dividing and conquering the domain and representing your functions with, again, now I'm limiting myself to piecewise constant functions, does have a meaning. So if you understand this one, this idea of, okay, so this is the best first function to choose. The second best function could be either this one, or I don't know, or something that looks like that, or I mean, whatever other smooth function that you can think of, but the question is then, how should it go on? And this is what we should be thinking of. So if you have the standard basis function, and the standard basis function would always give you for two elements, okay? So it would be this guy and then that guy. And you always get two of them, then it's fine. But if you know that you would get one at first and then the other, then probably first choose the constant. And the second one would be, I don't know, would be either this one or that one, or just the second one. Any combination of the two would allow you to solve for all piecewise constant functions on between 0 and 1/2, and 1/2 and 1. Okay, and this is really important. Now, if you got that, then the rest of what I'm going to talk about, at least in the next, I would say, half an hour, is quite trivial. Why?
But still, I don't understand why it's better, because the standard basis, I think.
It's not basis. Wait. It's not a basis. We said orthonormal functions.
Okay. Yes. Okay. So the standard orthonormal functions are the easiest way to create one function that represents the original function, because you just literally split the range to n areas, and then take the appropriate function from the standard and multiply by the Makadem.
Yeah, coefficients. Sure, you're absolutely right. So if I'm about to represent all my phi t's, which are piecewise constant functions that look like that, okay, then taking the full basis would be the best way to go. Okay, why? Because it's good enough. And again, remember that all these changes are happening at exactly delta i's. Okay, so if this would have been my functions, and I would have had to represent them by this set of orthonormal functions, then I know more than that. I know that this would be a basis for these functions, for the piecewise constant functions that change sign every delta I, because I can represent all of them with a standard basis. But then this is not a question. Even for this limited set of piecewise constant functions, I can do much better. In what sense? In the sense that now I'm not giving you the family as a whole. I'm telling you, you're allowed to use, assume that your channel at home, you don't have cyber hot, but rather you have some hot like I do, and you're allowed to have 1 bit at a minute, okay? So now you cannot use all the functions. You're allowed to use only 1, 2, 3 of them. What would you do? And probably the best way to go is just to transmit, first of all, the average of the whole signal. And therefore, you would manipulate somehow your standard functions into a different one. We call them f I of t. Okay? And the question is how to do it in the most clever way. And clever should be optimized with respect to something. And the something is optimizing for the, we mentioned that there is this error which is called the MSE error. And the more coefficients that you have, I mean, the more functions that you have, the smaller the error would get. And at the end of the day, all the functions that you would, I mean, all combinations, all unitary combinations of these beta functions would give you the same number. So when you have the capital N functions, you would get to the same error. The question is not the final solution, not the final result, but how you get there. If you're using the betas, the standard basis, then probably you'd get something like that. Okay, it would go down. Eventually, it would come to this location, and everybody would be happy. But I'm telling you that if you would get a different kind of functions, then for most probable psi of t's, what you would get is something that goes like that. Okay, it would go much faster, occasionally, in a moment we'll see, it would meet the standard basis. And at the end of the day, obviously it would meet it. But in most other cases, it would achieve a much lower error. And this is what you would like to have.
So what actually I was missing that you have to choose only some of the functions, which always now.
Going back to Barak, you don't choose the functions, you order them. And once you fix the order, you're allowed to transmit only the first n of them. And this small n is smaller than the capital N that you have to begin with. So you're absolutely right. If all I have is just linear combinations of these functions, then it would be the same. You'd get to the same final point. And this is important. So you've done nothing. You're absolutely right. But if the new game is now ordering them a priori, and picking only the first small n ones, not small, picking just the first n ones, then the question is how to reduce the error in the most efficient way. And this is the name of the game now, okay? It's all about representation. It's all about representation and choosing the coefficients in a clever way. Okay, so if you got this idea, and this is the name of the game now, so let's continue and see what is going on here. So we have our function, our smooth function. First of all, we represent it with the standard set of functions with we call it beta standard. And then we know that the function, the approximation of the function, we write it with a small hat with respect to the standard functions equals to the inner product of the function on the standard functions times times each of these functions. Okay, so each of them is hovering about, is having the support about a specific delta I. And obviously this is time, so this is a function of time. Now, the next thing that we will do is do the same trick, but now representing them with the Hadamard-Walsh set of functions. Okay, so we take the betas, the standard betas, and we, so this is all the standard betas now here as functions, and we take the Hadamard-Walsh function, unitary matrix, and we apply it to these guys, and we get these functions. Okay, the functions that we have plotted before. Now, the question is, what is the relation between these two guys? I mean, what would be the error? And it appears, I mean, Liran has the, I mean, if we chose n to be, capital N to be here, then what would be the difference between these two functions?
Zero.
Zero. Okay, thank you. So if I'm taking all of them, there would be no change whatsoever between the two functions. But the game would become interesting when I would start limiting the number of n to a smaller number. Okay, so let's see that what we are saying is indeed correct. So this is just multiplying the standard basis by each of the functions, and write it as such. And we, in fact, what we can do is plug, instead of the identity, plug in the Hadamard-Walsh, and what we get is that we get exactly the standard coefficient in the Hadamard-Walsh that are being presented to other coefficients, and here we have the Hadamard-Walsh functions, and we get exactly the same. So this would be equivalent to the psi of Hadamard-Walsh, let's write it like that, of t. Okay, so we did nothing. Again, choosing n would get us nowhere by permuting, by scribbling the standard functions. But and this is actually saying the same thing. Okay, so by definition, these are the coefficients, and we also have the relation between the coefficient of the standard functions and the Hadamard-Walsh functions. Okay, it would be nothing but the Hadamard-Walsh matrix that multiplies this coefficient from the left. And what we have is that relation between the standard coefficient and the Hadamard-Walsh ones is in fact what is written here at the top. So this is the relations between the functions, and this is the relation between the coefficients. Not a big surprise because we have seen it before. What else do we have? So we have that indeed the standard approximating the function with a standard basis is what is written here, with the is equivalent to the Hadamard-Walsh, and the Hadamard-Walsh represented as such. And since we know that the Hadamard-Walsh is equivalent to identity, then we have that indeed nothing has happened. I mean, as you said at the beginning, picking up n coefficients, we get identity between the two reconstructed functions. By the way, both of them would not be identical to the original one, okay? Why? Because we projected it onto a set of capital N functions, and we cannot necessarily represent any given function. So we didn't achieve much. We ended up with the same functions, but the coefficients are different. Again, by the unitary property, we have that this is the relation between the standard and the Hadamard-Walsh coefficients. And again, we get it into both directions. So this is taking the Hadamard-Walsh and translating into the standard basis. So what do we do with that? So the question is, why bother, as before, if the MSE, if the mean square error is the same? But now comes the question of what happens if we don't take all the coefficients, but rather truncate them after capital K. So not small n, but small k, okay? So now what we do is represent my coefficients. I mean, represent my function. Just remind me to add t here by projecting only to the first k, and k should be smaller than capital N functions. And if I do that, this is what I would be getting. And now the relation would not be as simple as before, okay? And we do the same trick, we apply the same trick for the Walsh-Hadamard. So again, we project it onto the first k elements, which is projecting the function into the first k functions. And this is how it is being written explicitly. And now the question is what would be, and again, there should be time here. And now the question is what would be the relation between the two. And what we are interested is basically is the norm of subtracting phi t minus phi standard, picking up the first k, compared to this guy, which is nothing but taking 5t minus psi, and here it could be the Hadamard-Walsh t. Okay, this is what we would like to do, and we would like to do it in an MSE sense. Okay. And it would not be a great surprise that what we'll get at the end of the day are the energy, squared energy of the signal, from which we subtract the projection onto these elements. Why? Because we have seen it for any set of functions that we have done, orthonormal functions that we have done, so it would not be different here. And now the question is which set of coefficients, those or those, capture more energy of the signal. Okay, this is the question that we have to analyze when we are blending, when we are designing our new functions. Okay, so what would be the MSE of partial representation? So not a big surprise, it would be the energy of the signal minus the projection onto the standard beta functions. Or in the Walsh-Hadamard, it would be the energy of the signal minus the projection minus the coefficients of the Hadamard. Okay, so these are the two that we have to compare between. We need to understand which of these coefficients, those or those, capture more of the energy of the signal. And again, if we know anything about the signal, this is where the game becomes interesting. Right now, we know that this is a completely random signal. So if k equals n, we have seen before, then both of them are equivalent. okay? Because then it would be just the projecting onto the piecewise constant functions, and it doesn't really matter how I blend them, okay? Why? Because if I look at the energy of those, it would, this is by definition how it looks like. I can plug in the unitary matrix that translates between the bases. Okay, so this is by definition the Hadamard-Walsh coefficients, and this is by definition the Hadamard-Walsh coefficients, and at the end of the day, we get the same energy. But as I said before, we are not interested in what happens at the end, but how to get there. How to get from the original error, which is captured by the energy of the signal when k is equal to 0, to the MSE. Okay, to the case where k is equal to n. Okay, now obviously, if we pick the standard representation, I mean, if we pick the ones that look like that, then obviously it should be this should start when that guy stops. Then what happens is they capture really well the local behavior of psi. I mean, especially at the beginning, and we have to add more and more functions in order to see what is going on at the end of the signal. The end meaning if we treat the time as beginning and end, then end would be, so this would be the beginning and this would be the end. So picking the first k would just lock onto the first part of the signal. The end part of the signal would have zero support. While for the Walsh-Hadamard, the first coefficients, I mean, if you look, just the first one would be the average of the signal over this interval, because the first Walsh-Hadamard is a constant. And this is the best MSE estimator for uniformly distributed signals. So something good is happening here. We have been able to somehow cheat the system in the sense that with a single function, we have been able to do the best possible way, okay? And now, how do we continue from here? Okay. So this drawing, let me just pick up that I'm not missing anything, should be exactly as what we did until now. So we've done it so many times, let's do it again. What we had here at the beginning of the signal, I mean, if I'm drawing this guy, so the psi, and it doesn't really matter at the beginning, the MSE, here at this point should be nothing but the energy of the signal. So it should be nothing but integration over psi t square. Okay, this is where we draw it as k here. This is where k is equal to 0. Okay, and where k is equal to n, the error would be nothing but this guy minus the sum of the coefficients. Okay, so we mentioned that as psi beta, for example, I equals 1 to n, and it's important that this is 1 to n, and it would be the same for both. But if for the for the standard basic, it would have gone like that. Okay, it would go like a function that goes like that. For the, so this is the standard basis. So this is beta s. For the Walsh-Hadamard, what would get is something probably goes like that. First of all, the biggest decrease would be here because we are choosing the constant in order to represent my whole signal. Now, there should be some points, in a moment we'll see, we'll explore exactly which points where I would have would have this kind of identity between the two. They should and they would somehow align. But in the rest of the process, and here, for example, again, and then it would get here. Okay, so this would be that guy. So this would be my beta Walsh-Hadamard, or Hadamard-Walsh. Okay, so And what we care about is, again, is how we get there. I mean, we would like to reduce the error in the most efficient way, and this is what we care about as a function of k. Okay, so this drawing should now be at the background of your brain when designing new functions. So let's see how to do that. Now, remember that I mean, now we are at the point where we would like to represent a given function, and all we know is not much about this function. All we know is the range of values that it is getting, and the fact that it is a mapping, I mean, that it is defined on 0 and 1. Okay, so it gets some values. This one would be the highest, and that one would be the lowest. And this is what I know about the signal. And as we already said, we know that the best number to capture this function between 0 and 1 would be the average. Okay, so this would be the first one. Now, and this is an assumption that we will probably, I will not break so soon, but this is an assumption that makes sense. Then what we would like to do is somehow choose another number that would best approximate my function in these two intervals. Okay, so assume that somebody is giving me two numbers to represent my my function. So what I would, and I cannot order the set of numbers that represent my functions. So what I would do is I would split my domain into two, assuming that the distribution of the function is random no matter how I do that. So this is an arbitrary selection, and say that this part of the numbers would be represented by one number, and that part would be represented by a different number. Okay, so again, having two numbers at hand, this is what I would like things to happen. And in fact, if you think of the standard basis, this is exactly what it is doing. Okay, so the standard basis would give you one function here and another function there, and these functions will basically give you the average of these numbers and the average of these numbers. But, and this is an interesting but, in fact, any unitary combination of these bases would actually do the same. Why? Because we have two equations with two unknowns, so we can always solve them. Okay, so in fact, any non-trivial combination of the two would in fact give me the same construction. Now, what we would like to have when we're talking about multi-resolution is to next approximate over these intervals in the best possible way. And in the n plus one iteration of my story, I would like to find an approximation over these kind of intervals. Okay, so what I do is, first of all, I divide my my domain into 2, then into 4, then into 8, etc., etc., etc. And I would like to have the best possible way of representing my signal over these intervals. Okay, so and as we said, for the best MSE, the best estimator over any interval is nothing but the average. Okay, so this is something that we know. How do we take this obvious observation and construct a set of functions from my standard function? Or assume that the only events that may happen is that in these intervals I may have my bases. I can allow my bases to change. And the question is, what should I do then? And the answer is that if at the stage, so this is at stage n plus 1, or n is some power, or capital N is a power of 2 to the power of n, I have n numbers that should approximate psi of t. These are the intervals, and these numbers are the standard representation if, for example, I choose them, and this is how the approximation should look like. It should be nothing but the projection onto the standard functions times the standard functions, and this is how it looks like. So this is the best way of piecewise representing a function in these intervals. And I'm repeating this story so many times, so by now you should be familiar with that. Now, in order to provide a multi-resolution construction to what we have just said, we need that this optimal reconstruction would be valid for providing one number. It would be valid for providing two numbers. It would be valid for providing four numbers. And in fact, it should be valid for providing 1 plus 2, which is 3, 1 plus 2 plus 2 to the power of 2, which is 7, etc., etc. Okay. And the question is, can we do with less numbers, exploiting the notion of successive levels of representation in the resolution? So if, for example, we just have the constant, I mean, we just multiply by the constant, in order to represent the next resolution, do we need to supply two projections, I mean, projection into two functions, or should one projection be enough? And it appears that one projection should be enough. As I said before, any linear combination of at least for the two-dimensional case, it is quite obvious. So how do we do that? How do we do something constructive out of what we have just said? So now, to make things a little bit more complicated, what we do is define my time interval between t low and t high. So this is an arbitrary interval. And we define the interval to be delta L. Sorry. We define this part of the interval to be delta L, and we define this part of the interval to be delta high. Okay? And the question is how do we approximate the function? And in fact, we can average the function at this interval, and we call it the optimal approximation of psi in the low interval. And this guy would be, here it's not conjugate, but rather optimal. And here, this would be my psi at the high interval, okay? And we know that if we have a representation of psi in the low interval and a representation of psi in the high interval, obviously the average of the two would give me the average over the whole interval, okay? So the average of the whole interval would be nothing but taking psi at the low interval plus psi at the high interval and taking the average of them. But if it works in this direction, believe me, it could also work in that direction. I mean, it's enough to just have the average over the whole interval and the average over the low part of the interval in order to extract the average at the high part of the interval. Okay, is that clear? It's almost a tautology because we have exactly the same number of equations as number as and on, which is 1 and 1, so it should be obvious. So given psi at the whole interval, we need only either the low or the high, or any non-trivial linear combination of the two to obtain the three of them. Okay? So this is the only claim in this relatively complicated slide. And now we will take it to the limit. So if we have an optimal approximation of the finest resolution, okay, so now assume that we have all capital N numbers at the finest resolution, we could produce by averaging the representations at any lower resolution. So getting from high resolution to low resolution is trivial, okay? But we would like to invert the process. We would like to start from the coarse resolution and then somehow propagate our ways into the fine resolution and still keep the same number of coefficients, okay? So the high resolution coefficients are those that you have over here, which is nothing but the projection of psi and the ones, and everybody's happy. So again, just writing it again. So we are considering these kind of numbers. And what we'll do now is just manipulate these numbers. Well, let's do it one step at a time. So at the n+1 level, what we have is 2 to the power of n numbers that we represent as such. Okay, these are the coefficients of the numbers that we have. Now, if we go one resolution higher, lower to a lower resolution, so this would be the 2 to the power of n minus 1 numbers, then what we need to do is average each and every couple. So now what we need to do is just average each and every couple. And if we go to the next resolution, to a coarser resolution, then what we need to do is average 4 coefficients. And if we go to a coarser resolution, then what we need to do is average as many numbers as the number of resolutions that we have. And in the coarse resolution, in the coarsest, what we need to do is average all the coefficients, and they would give us the average of the signal. So the average of all coefficients would give us the average of the signal. Now, if we plot it as a tree, then what we have here is capital N numbers. And then what we do is we couple each and every 2 of them into a single number. And then, and obviously it continues, and then we couple each and every 2 of them into a single number. And at the end of the day, at the root, what we have is the average of all the coefficients. And the question is the following. In order to capture all the numbers in this tree, how many numbers do I need? Okay, so obviously, if I pick these capital N numbers at the bottom, I can do very well. But the question is now I'm telling you that there is some order by which you can transmit these numbers. So probably I would like to first of all hang on to the root of the tree. Okay, and from the root of the tree, and this number, so let me just change the color. So at first, what I do is just keep the root of the tree. Now the second number would be this number. So from this number and the root of the tree, what I know is how to deduce this number. Okay, and then the next number that I would have is the root of the tree, and in the next, so now I have all these numbers by keeping only these two numbers. Now, how do I continue? Probably what I would like to add right now is a way of splitting this part of the tree and that part of the tree. So probably providing this number and that number. So I have to add 2 numbers. And then in order to split, and then I can, so these are the numbers that I would have. And these numbers I can actually compute. And this is how it continues. So now in order to split this part of the tree, in order to split this part of the tree, I need to provide this number. So I can deduce, I can compute this part. And obviously I have to provide that number, and I can then compute this one. And I have to provide this number. So I can compute this one. And at the end of the day, what you will see is that the number of coefficients that I would provide at the end would be n divided by 2 plus, here I need only half of the coefficient, n divided by 4, etc., etc. At the end of the day, it would converge to n minus 1 or something like that, okay? So at the end of the day, I've provided the same number of coefficients, but the order by which I provided them allowed me to, first of all, capture the coarse resolution, the constant, okay? Then the next one allowed me to split my domain into 2. Then the next 2 coefficients allow me to split my subdomains into 2. The next 4 allowed me to split my subdomains into 2, etc., etc. Questions about this kind of construction? If not, then let me just tell you that this is exactly, so the tree that I've now painted for you is exactly what is going on here. So now, brutally, what we do is jump to the kth level with n with 2 to the power of k minus 1 numbers. And the question is how many numbers, and we know all the coarse resolution. And the question is how many numbers do we need in order to completely span the whole 2 to the k elements? And the answer is that we need only 2 to the power of k minus 1 additional numbers to produce the optimal representation at level k plus 1, okay? If we start at level k. So what we actually end up needing is 1 plus 1 for the next level, plus 2 for the next level, plus 4 for the next level, etc., etc., that sum up to 2 to the power of n. So we end up, again, producing exactly the same number of coefficients, where, again, we know that the whole is equal to the average sum of its parts, okay? And we also denote the difference between the two parts as that. So if this would have been my whole interval, and this would have been delta L, and this would have been delta low, then the estimation of psi here minus the estimation of psi there, so this was high and this was low, the estimation of psi here and the estimation of psi there would be the diff. We call it the diff, okay? Why? Because the diff and the whole, I'm calling this the whole, and I'm calling this the diff. The diff and the whole would allow me to construct a multi-resolution tree or a multi-resolution construction of my coefficients. So if the whole equals to the sum of the left and the right, and the diff equals to the subtraction of the, here it's called left and right, okay? Left and right. And this one is equal to the subtraction of the left minus the right, then we can obviously invert this equation, and then we get that the left and the right are equal to nothing but the whole plus the diff. Okay, so the whole plus the diff is equal to the left, and the whole minus the diff is equals to the right, to the average on the right. Okay, so this is the way of traveling in my tree so that I can use the root and this left in order to reconstruct the right. Okay, and then the root and this left in order to reconstruct this right. And now I need to provide this number in order to reconstruct this guy. And the way to do that is by having is not just keeping the values of the vertices here, but rather keeping not just the vertex, but rather keeping the difference between these two. So it makes the whole construction a little bit more symmetric, if you wish. So here I don't keep this value, but rather I keep the value of this one minus this one. Okay. So in a sense, we are living in between the vertices of this tree. Let me just pick up a different color. So it would be living somewhere in between. So this would be the diffs. The diff. And in fact, also the whole. And the whole is that. Okay. So if we start from the highest resolution, then the first thing that we have is the average. And then the diff would be taking the first half and subtracting the second half, okay? So again, this is my whole interval between 0 and 1. I'm taking, this is my function. I'm taking the function and hitting it with a constant, and this would give me this number. So the inner product of psi with a constant over the whole domain would give me this average. And then what I need to do is just compute also the subtraction of all these coefficients from all these coefficients, and this is how it is done. I'm just multiplying the coefficients by +1 for this half and then -1s for that half, and this is where I would get the first diff from, okay? So from these two numbers, from this number and this number, from these two scalars, what I can extract are the averages in the next layer. So again, I have the average over the whole domain, and I have the subtraction of this average minus that average. And now obviously what I can get is the average at each and every interval from these two numbers. So in two numbers, I got 3 intervals, the whole, the left part, and the right part. And I continue this constructive story iteratively. And I already drew the tree, so checksum here. Now, how do we do it in a matrix form? So now I don't know about Walsh, I don't know about Hadamard, and I would like to construct my own matrix in order to do the game. So what I would do is the following. First of all, I'm keeping the sum of the whole. Okay, so this would be multiplying the standard coefficients by ones. I'm just summing over all the coefficients, and this would be the first sum. And the first diff would be nothing but taking the left 4 minus the right 4. Okay. So this would be the first D. So in my tree, I've computed this guy, and I've computed that guy, the difference between the left and the right. Okay. Okay. Next, let me just. Next would come the D left and the D. So next, I'm observing this part of the tree, and I would like to look at this guy plus. Sorry, so this would be the sum. Okay, so here I can actually get the sum from these two numbers, from the diff and the whole. I can get the sum here. So what I need to do is compute the diff for these two numbers, and the diff for these two numbers is what is written over here. Okay, so it would be the diff for these two numbers. Now, next, what I need to do is add the diff for these two numbers. And the diff for these two numbers is captured by this part. And this would continue. Now I have to split this part of the tree, which would be captured by that. That part of the tree, this would be the diff here. That part of the tree, that would be the part here. And that part of the tree, that would be the part here. Okay? And obviously, I need to have, if this is my basis, it needs to be normalized. So the normalization of these two guys, should be 2 to the power 2, 1 over 2 to the power of n. These two, I mean, you just have to sum the number of ones that you have here, and this would be the normalization, etc., etc. Okay, and the last one have only 2 coefficients, so it should be normalized by 1 over 2. So what happens is that my if I'm looking at the at this D matrix, okay, so this D matrix would be my normalization factor, and this would be a matrix of ones. Okay, so if I couple them together and call this one M, what I would like to verify is whether this M is indeed unitary. Okay, because we said until now that by unitarily permuting the standard basis, I can create new orthonormal bases. And obviously, we see that this basis is orthonormal. So would it be true to claim that M is unitary? Let's check it out. Let's compute M times M transpose. So M times M transpose would be D, okay, times, now I need to be careful here. So these are the diagonal weights, okay, and the diagonal weights times the matrix is defined as M. So this is capital M. And now I have to multiply M times M transpose. So this is M. So this is D. Then I have M times M. I don't know how. Oh, okay. So this would be the, if I take only this part and I call it Q. So this would be Q times Q transpose over here. And there would be a D there. Okay. And we see that this part is the identity. And because this part is the identity, what I end up with is with an M which is not unitary. So we say that M is almost orthonormal up to multiplication of M by this D factor. And what can we say about it? Not much. I mean, now again, until now we defined the Hadamard and the Walsh-Hadamard, and now we are ready to define another family that would be that would have the nice properties of being orthonormal as well as orthogonal in a sense. So let's try to do that. So let's define the Haar family, and the Haar family would go like that. This is how you define it. First of all, you define the most basis member of this family, which would be 1, 1, 1 minus 1. And then the way of constructing the next layer is taking the Kronecker, the Hadamard product of this H with 1 minus 1. So it would mean copying H to N and H to N here. And here it should be identity times 1 minus 1. So here there should be identity, and here there should be minus identity. Okay, so this is how you construct the next level of my Haar family. Now, how would the Haar family look like? This is how the first one looked like. So the first one would take the standard basis and would reduce the average. The next one would be the diff. This is really what we like. And this is how it would look like for the H4. So for the H4, what we have is the, okay, so this is different. What we have here is the 1, 1 are being placed at each and every point of the Haar matrix. So instead of this one, I'm replacing this element by these two. Okay, and I'm replacing this element by these two, etc., etc. And then what I would do is replace each and every identity here with these two numbers. So there should be an identity here and here. So I'm replacing the identity by these two numbers. And 0 times these numbers would give me this one. Okay? So this is how the Haar family is being constructed. What we see here is that here we have 1 sequency, here we have 2 sequency, and here we have, I mean, it depends how you relate to it. We also have 2 sequency in the sense. I mean, and the question again is how do you refer to that? And this is how the Haar H8 looks like. So here we have a function like that. Here we have a function that looks like that. Here we have a function that looks like that. And in a sense, it is very similar to the multi-scale construction that we have worked with before. But now, rather than, okay, so let's continue with that. Okay. So again, this is the Haar family. This is how it looks like, and it seems to do the right thing. Now, can we prove orthogonality for the Haar matrices? So this is really tedious, and I hate it. So what I will do is just walk with you with the first steps, and then do something like that, and go out to the conclusion that the Haar is indeed an orthogonal matrix, and therefore it is unitary. And the way to prove it is again by induction. What we do is we take the previous Hn, we assume that it is orthogonal, and what we do is we construct the next one. So this is the construction of the first one, transposed, and this is the construction of the second one. Okay. When we put a line like that, it means that here I basically put the identity because I have to take the conjugate here, so it would be the transpose. So this is what I'm taking here, okay? So again, instead of each and every element of the identity matrix, I'm plugging this part. Instead of each and every element of H, I'm plugging this part, etc., etc. And now what I would do is use the Hadamard multiplication rules in order to open this multiplication of matrices. And at the end of the day, what I would get is something that something like the identity times something that looks like the identity. And if in the identity I take each and every element, so here I have ones, and instead of each and every element I introduce something else that looks like an identity, I'm just doubling the size of my identity, and 2 and 2 cancel out. And at the end of the day, what I'm getting is this identity. So assuming that hn, that h to the power of n is unitary, what we end up is a proof that the next one is also unitary. Okay. Here we use the unitarity of the previous one in this part. Okay. Okay, so this is happy, and please go over this proof. It would allow you to understand a little bit what is going on with the Hadamard product. Hadamard or Kronecker product. This is this guy. Okay, I think that in MATLAB you have it like cron, if you like to use this this command in MATLAB. So this was tedious, but now we have a way of taking the standard basis and doing something useful. So let's use it. So if we use it, if you use the Haar matrix, is it actually unitary? Since the Haar matrix is not symmetric, in spite of the fact that I have this one, I don't have that the conjugate is equal to the matrix itself. And therefore, I cannot write that. So the Haar matrix is not symmetric, and therefore I cannot write that equation. And I mean, multiplication of the Haar matrix itself would not give me the identity. And so you just need to remember that it is important to take the conjugate or the transpose and to use it properly. Now, if I apply to the standard functions, then it would immediately define for me new functions that we call the Haar functions. And the Haar functions, if you look at them, would be the constant at first, then it would be this guy, then that guy. Remember, there is a 0 here, then that guy. And you see that something interesting is happening here. Okay, that we are able to do something that looks like in the spirit of my multi-resolution construction. So I've just plotted it, but let's do it again. I mean, the first one would just be the constant. The second one would be constant and then minus. Just go over it again. So it will be constant until the center and then -1. The next one would be 1, -1, and then 0. So this would be -1. This would be +1. Okay, this is +1. And the next ones, and this is +1, obviously. And the last one would be 0, 1, -1. So the last one, let's bring the grid on, would be 0 until the center, then +1, then -1. Okay, so this is the first, the second, the third, and the fourth Haar. So this would be Haar 1t, Haar 2t, Haar 3t, and Haar 4t. Okay, and so this would be my four functions. And if I continue, I mean, I can have a higher order of Haars, then I would have even more interesting functions, multi-resolution functions to work with. And again, what we can say is that if we pick the n the full n numbers, then representing psi with the standard functions or with the Haar functions, I would get the same approximation. Okay, and this is exactly as we did before. We plugged in the standard definition the identity, we split it into the Haar generators, and at the end of the day, what we get is that these are the Haar coefficients and these are the Haar functions, and we get exactly the same representation. Okay, but as mentioned, so again, this is just saying the same in the same. I mean, this is just basically saying the same. So again, if we choose n equals 2 to the power of n, this would be the game. And in fact, if you will notice, this would be the case for any n to the power of, for any n which is equal to the power of n, no matter how many capital N I begin with. I mean, it should be also true for n equals 1, 2, 3, etc., etc. So if I take my k to be 2 to the power of n, I would probably get that psi k using the standard basis would be identical to psi Haar k using the standard basis. Okay, this is just for these numbers. Why? Let's go back for a minute to the way that the Haar was constructed. If I look at how the Haar was constructed, so let's look at the 8. What I see is that until this level, I basically done everything to the resolution of twice the signal. Okay, I did it in a different way. I mean, this is captured by these two. So all these guys are, I mean, constant values at these intervals is something that I can reconstruct with this interval. Okay. So if I have a standard basis which is equal to 4, using the Haar up to this point would have been equivalent to capturing my my signal with a standard basis of 4 elements. But the Haar construction continues. It allows me to continue and refine my representation, and at the end of the day, get a representation that would have been equal to representing the whole signal with standard basis of 8 elements. Okay. And if we go back to this part, what I did now is allowed myself to split my domain into 2 regions. So at this point, representing my signal with only these 2 coefficients of the Haar would be as if I would have had the standard basis with only 2 elements. Okay. Or let's write it as beta. Okay. So what I'm saying, let's do it in a more orderly fashion. What I'm saying goes as follows, is that for the Haar, what we would be getting I mean, the Haar basis, let's plot the Haar basis. Okay, so the Haar basis would look like that. It would look like a constant. So if this is T, so this is how the first basis of the Haar would look like. Then the second one would look like that. It would be 1 until the middle, and then it would be -1. The third one would be 1, -1, and then it would go to the 0. And the fourth one would split the rightmost interval, so it would be like that. Okay, so this would be Haar 4. So this is the first, the second, the third, and the fourth. Okay. Okay, so now the question is, what do we do with that? So now this is an exercise that we have done so many times, so we can just jump to the conclusion, and the conclusion is nothing but saying that the standard basis is nothing but representing, I mean, this is taking the Haar coefficients and the Haar functions, and what you have is basically the same for the nth element. They would just align, so there is not much to it. And at the top, what we have is the definition of the standard basis, and now we plug in the Haar functions, and at the end of the day, what we get is that the standard coefficients are equal to nothing but the Haar matrix that is multiplying the Haar coefficients. So we have this relation, which we have seen so many times before. But what would be interesting is to explore the MSE. So now let's mean square error analysis for the first case, for the first k terms of my representation. So there is this theorem that is allowing me to say the following. Let L be equal to 1, 2, 3 to n. Then if I'm looking at the Haar coefficient at the level k, which is equal to 2 to the power of L, then it would be exactly equivalent to the MSE error of representing the signal with a standard set of functions, where the standard set of functions is equivalent to k. So it would be a k split of my domain. Okay. What I'm basically saying is that exactly what I said before is that if I'm looking at the first two coefficients, it would be like representing with the Haar coefficient, it would be like representing all piecewise constant functions, which is something that I can capture with the standard functions. If I'm looking at 4, then the Haar would accurately capture the 4 piecewise constant functions. And again, the same would be, I would be able to capture with beta standard 4. And so on and so on and so forth, okay? So this is yet again the same proof that we have done before, so there is no point of proving it yet again.
Can I have a question?
Sure.
What is the motivation to use Haar family over Walsh-Hadamard or the other way around?
Remember that in the Walsh-Hadamard, okay, so first of all about the Walsh. The Walsh did not have my way of being able to construct the sequences in the right manner. Okay, so I had to resort, and then I've told you that there is this Walsh-Hadamard that is allowing me to do something, and in the Walsh-Hadamard we got to something which I had a problem with because it had some fishy properties when I started exploring the way that the matrix that generated it was performing. Then I was talking about some multi-resolution way of constructing a basis and forcing my values to always have +1 or -1 values. I had some difficulty with that. Again, my M function had some deficiencies that I wanted to get rid of. The best from the nice properties point of view was the was the Haar functions, because it was both orthonormal, I mean unitary construction of the standard basis, and beside that it also satisfies the construction that allows me to split my domain each and every iteration on one hand. Now, what are the benefits? What are the pros and the cons? Let me go over way that it is constructed and tell you. Look at what is going on here. If I'm splitting my set of L's or K's or whatever you'd like to call it into these domains, so I have the first two, everything is fine. I have the, and it's the same almost everywhere. But now the next K, the next two elements that I have would just do the following. The first one would just split the first element, and the second one would just split the second element, okay? Now, the next four would split the first element, the second element, etc., etc. So there is, within each interval like that, I'm sequentially splitting my elements in the tree. Now, this is regarding the har functions. If we would go back into the previous ones, let's go back into this kind of Walsh-Hadamard. Then here the story is a little bit more interesting, okay? So here there is a sequence of events that is happening, and okay, so the first two are the same, but then the next ones are splitting my domain into at points which are in some sense, I would say, well distributed over my data, okay? And the same goes on and on, okay? So here I'm actually, and here again, here I'm not using the zeros, okay? So here, without using the zeros, there is some nice property of the way that the data is being distributed, okay? But I will not be able to claim at this point or at any point that I'm being equal to whatever would have happened if I would have represented my signal with the basis, with the standard basis, okay? With the Hadamard, sorry, so with the har, this is with the Hadamard. With the har, I can. With the har, if we go back to the har, with the har I can. With the har I can at this point, well, it was exactly as before, but at this point I can say that you would be equivalent to psi 4, and I mean psi with a standard 4, and at this point, well, it is obvious, but you can actually continue with that and it would always apply. So with the har, you can actually show equivalence to being able to represent with a standard basis at a specific resolution. Okay, so this is regarding the har basis, and this one we saw. That sounds we've done so many times before, so I will leave it to you now. I think that we are almost done. The same thing that I've done before can be done from bottom up rather than top down. And this is the same idea, basically. If you think, I don't want to go over the details here because they're not so important, but if you go over the subdivision way of looking at your signal, so you have this binary tree of elements, and remember that we said that by just representing the average, and then the diff, and then the diff of the two, etc., you can actually capture the whole value of the tree. Then you can also work it up from bottom up. It's not so important, but just that you know that there is an alternative proof to the game. So if it would have been really vital, I would have stopped and talked about it. But at this point, I think that we have enough motivation to ask more fundamental questions. And this is okay. So you showed me the standard basics. So the standard basis. So somebody gave me this standard basis and told me this is my building block, my building blocks of my signal. But now remember that this building block allows me to represent only functions. I mean, accurately, only functions that belong to the piecewise constant set of functions, and not just piecewise constant, but rather piecewise constant that change their constant at the delta i's locations, okay? And this is a really poor way of representing signals. I mean, it's good, and we have seen a constructive way of doing it in a multi-resolution fashion. And the question is, can we do better? I mean, can we enlarge the set of functions and the set of representations that we are allowed to represent? And again, the game would always be the same. Assume that you have a family, a large family of n functions, of n beta functions, beta of t. And now I'm allowing you to use only small k or small n of them. How would you design these functions? And now the question is, what do we know about psi? If it would have been piecewise constant, so that the constants are changing at these intervals, then I know what to do. Otherwise, let's wait for the next lecture, okay? So I've seen that Tom is answering all your questions. If you have any further questions, then just let me know, because I'm not monitoring the bits and bytes of what is going on in the discussion group. And if you don't understand anything, please jump in the middle of the lecture or do. I mean, it's really easy because we are not so many students, and it's really easy to do that with the Zoom. Okay, so any questions?
Yes, I have two kind of abstract questions.
Okay.
The topics of today reminded me two concepts, one from probability of moments and one of the Gaussian pyramid.
The Gaussian?
Pyramid.
Okay.
I wonder if it is connected, how it is connected.
So Gaussian pyramid is some heuristic way of looking at an image. You take an image, you convolve it in a moment when you take the average of the whole image, and then you get one number, and then you split it into 4, and then you get, obviously it is related. I mean, you take a signal and you get this heuristic way of representing the signal. And then you really need to take care of what would happen at the boundaries between your averaging. If you do it and you don't take care of it, and this is why it is Gaussian. Gaussian is this kind of a function that gets 0 at your support, at the boundaries of your support. I mean, converging to 0. So if you don't take care of it, what would happen is that at the end of the day, you would have these artifacts that look exactly like a piecewise constant function. So it depends what you like to do. Networks, for example, neural networks really like this multi-resolution effect. In fact, they don't just average. So if I'm looking at my signal, and before we talked about the left and the right, they don't just average the left and the right, but rather they look at if I'm looking at it from a bottom-up perspective, let me just gain some white here. Then what they do is they look, first of all, they look at all the couples, and they don't look at the average, but rather than they look at the maximum, okay? It's called max pooling. Okay, and then for each and every 2, you do something in between, and then you also max pool. And at the end of the day, this idea of doing averaging or max pooling is called an encoder. And then you can scale it up, and it would be called decoder. And fundamentally, this is exactly the same question. How can I take my information here? And here I have a black box. Okay, this is the black box that we are now trying to understand and decipher, so that at the end of this black box, I'm getting this small number of coefficients that would represent my psi function. Okay, so here I have my psi beta, assuming that I have some functions here beta that are allowing me to represent my psi here. And then I also have a reconstruction mechanism that from these betas would allow me to extract back the function or something else. And this is called a decoder. So encoder decoder is something that we use, for example, in deep learning. So it is related. Yeah, just 1 second. ISO. This is what happens when you teach from home. Now, the next question is how do Gaussian pyramid relate to it? So Gaussian pyramid is sort of a linear way of constructing a multi-resolution construction of your image, and then you do certain things at low resolution and certain things at high resolution, and you can process your data. So yes, it is related. It is related also to this encoder decoder idea in neural networks. You mentioned something before the Gaussian pyramid. What was that?
In the probabilistic sense, the moments. We learned that the first moment is the average. The second moment is the expectation with the variance.
So here the relation is a little bit weak. If you have an object, let's write this object as a sampling of this object. I mean, assume that you have, let me do it the way I know it. Assume that you have an object in 3D, okay? And now you sample this object, okay? These are the points that are representing this object. And this object can be abstract or not. Moments are usually the sum over all the coordinates. This is the first order moment, okay? So the first order moment over all the xi's would be the center of mass. And indeed, it would represent best the object. The second order moment would be summing over the squared of the indices of the coordinates, okay? So usually the second order moment after you have subtracted from x, the first order moment would be the moment of inertia, okay? What are the main axes? If I'm looking, for example, at an airplane, so the second order moments would be this guy and that guy. This would be the main axes of the points that describe the airplane. And then third order moments, etc., etc. And if you take enough moments, you have your P of X of Q here, then if you have enough moments, the claim is that you can represent back your structure, your geometric structure. Okay, so the first order moments is just the average, so it obviously relates to what we are doing. So first order moments, you are there. Second order moments are in a way representing your data. And second order moments, you will see, relate really closely to PCA. In PCA, you treat the data as some Gaussian distribution. The average would be the center of mass, and the second order moments are called the principal components, would be nothing but your principal components. I mean, this would be nothing but your beta functions by which you're representing your functions, okay? So if this is the space of all possible functions, okay? So the second order moments would be nothing but your main axes that span the distribution of your functions, okay? So yes, it is related. In the PCA, we will see how it is related to moments of considering functions as a distribution. And this would be the autocorrelation, and then you diagonalize it and basically take these principal directions. Gaussian pyramid, obviously it is related, and obviously it is also related to encoder-decoder in the neural networks fashion, where over there you throw completely everything that we learned about, and you just have a black box that is called neural network. And you need to be a little bit clever about how you construct your black box, but at the end of the day, it would give you a small number of coefficients. And here you don't even have to have the same functions in order to do the decoding. It would give you back either your function or something else. So for example, here you may have a two-dimensional image of my face, and here you may have a 3D geometry that you learned from many examples. I don't know if I've shown you that example, but if not, you are welcome to look at papers by Elad Richardson that does something like that. So you can do magic with this kind of structure, but for the time being, let's keep things very, very simple. We don't have these neural networks. We have here a beta function, and we project and we reconstruct, okay? For now, all we do is reconstruction by projecting my psi input into these beta functions. Once you are proficient with that, only then you should continue to something where you don't know anything about the neural network. Believe me, without that, you lose intuition completely. I mean, it's really bad. I see that with engineers and scientists I work with. More questions? Yeah, they don't have to belong. I mean, they don't have to relate directly to the to what I'm showing you. I mean, you can ask professional questions. If not, then thank you, and we'll see you again next week.
Thank you.
Thank you. Bye.
Have a nice day.
You too.